Okay, now I'm going to go ahead and make myself my MinGW, not on the Ubuntu part, but on Windows, how I can install GLFW and glue libraries and compile my code. Okay, when we click on GLFW, it gets us to actually a zip file. Okay, so GLFW is available on Windows, so I think when you download it, it automatically detects your system. So I have this zip file. Let me extract it. So this is my zip file. There is include depths. So I think I need to, this is the source, I think, for, no, I should. So let's see, include source, test, examples, dependencies, CMake. So when I say include, yeah, the header files are here, glfw, h, glfw3 native.h. So what I need to do is, I need to copy this glfw directory completely and copy it under my MinGW x86-64. So the 64 bit part, so it's under include. I have this GL, but I need to just paste it here. Okay, continue. I need to have administrator access. So glfw include files are copied here directly. Now I need to have the libraries too, but let's see where those libraries are. Or maybe I make them myself. So module CMake. I think I need to compile it. They're not, they don't come pre-compiled. So MinGW is here, there are dependencies here. So how to, probably I will need, with MinGW I'll be able to do that probably. Tests, so there are some tests here, examples, different examples of GLFW, and let me read the README file. So where's installation? Compiling GLFW. Oh, there's also pre-compiled Windows binaries available for all supported compilers. Actually, I can go ahead and try to download this one instead of building on my own. I was looking for pre-compiled binaries, but yeah, it wasn't within this bundle. Oh, here, Windows pre-compiled binaries. So 64-bit Windows binaries. I download this one. Now I should have the pre-compiled libraries there. Let me unzip it here in this directory. Yeah, as you can see, there are different libraries. For example, if you're using Visual Studio, Visual C, there is different versions, Visual Studio 2022, and this is MinGW 64-bit. Okay, this is the one we are looking for. So there is a DLL file, which actually should go to your, I think, system directory, as with the other DLLs. But this GLFW3 and GLFW3 DLL, which is going to speak with the DLL file, these two, the .a files, should be put into your MinGW lib directory together with other .a files. Okay, again, I copied them. Continue. Okay, now I'll have this libglfw .a files in my MinGW lib. And this glfw3.dll, I'm going to copy this to my system directory where the DLL files reside. So this is, with this installation of glfw is complete. So system32. Okay, if you go to your system32 directory, you're going to see you have a bunch of DLLs here, and I'm going to copy this glfw3 DLL here, and that's it. So you're actually set for glfw3. That's it. I don't need to do anything else. I can just delete these temporary downloaded files I have here. Now the remaining thing I need to do is to install glue. So we are done with GLFW. Now let's go ahead and install glue. And again, there are binaries for Windows 32-bit and 64-bit. So it's automatically going to be downloaded from SourceForge here. And this one is just 32.zip. Let's see. It was saying 64-bit too, but let's see if we're going to have a problem with this. So it's a little bit larger than, yeah, but it's done. Let me unzip it also here. Glue 2.10. So again, I have the bin. Oh, as you can see, under release, there's also the 64 version. There's some executable files which you can use to test your system, OpenGL system, visualinfo.exe. So if you click on it, for example, it actually created a text file which tells you about which extension functions are available in your OpenGL driver. So OpenGL vendor string and media. So this glue was able to tap to my graphics card, find its type, find its OpenGL version. So the driver that is currently installed on my graphics card supports OpenGL version 4.6, and these are the extension libraries that is available to me. So these are really advanced functions, sample locations, extensions. So there are many extensions. I don't know what these are, but these are the functions that are available to me basically. There's also glue info. When I click on it, this is the glueinfo.txt. Again, glue version. So supported OpenGL versions. If you're using, for example, OpenGL version 1.3, these are the functions that you can use. GL multitext, GL active texture. All the OpenGL extension functions that are available to you via this one. Glue is written here. So it's running with no problem. So again, this DLL, which is this binary release, I'm going to copy this DLL on my system32 directory, which is here, program files and system, well, not program files, directly Windows system32. Okay, the DLLs are here. I copied also glue32 DLL here. Now, this was the binary release, the binary part, the DLL, and there is the include and lib directories. If you go to include, there's a directory named GL, which tells you that the glue, these header files, glue.h, they're going to be put onto in your MinGW here. Program files, code blocks, MinGW, include GL. So I don't have glue here. Now I copy them here. I have I now have glue.h here under GL. The only remaining thing here is to put the precompiled binaries here, the lib files, release, the 64-bit, these glue32 lib here. These two files, as you can see, they do not have .a extensions. They have lib extensions. MinGW should be able to read them, but last year some students had problems with these lib files, so we had a post related to that. Let me just show you from my email. Let me find that out. MinGW GLFW. So this was the compilation problem that I got. Oh, I think it was, this is the post, the GLFW linking problem. So the last year, MinGW could not read these lib files of glue, which were these glue32 lib, and these are the lib files we put here, right? Yeah, glue32. Although it's 64-bit, they're like its name is glue32 lib. So it wasn't able to. It's not .a extension, so he had a problem with these. So in order to solve this problem, there was this post about this linking lib files with MinGW, and also there is a utility which is much simpler to do, lib2a, which can convert those lib files to .a files and replace, just put them those .a files in that lib directory to have that. But let's see whether I'm going to have a problem with these or not. So I put them in the lib directory. I have now glue installed. I have under my gel I have glue.h, and here I have glfw. So everything, I think the setup is complete, and that's it. As you can see, in each of these installations there are three components: the DLL part, the library part, and the header include files, header files. So you put the header files in your include file in MinGW, and also you copy the lib files into the lib directory, and the DLLs go to your system32 folder. Now let me delete these temporary files too. I did all the copying, and hopefully I will be now able to compile my test program. So for that, I open a shell prompt, okay, and you can use PowerShell if you want, but the regular command prompt will also do. I go to desktop, it was in glfw examples, okay, so here is my test. Now I'm going to compile it. I think these are just C programs. I have test.c, so I should be able to have this GCC. By the way, the first time you download code blocks and MinGW, your environment, path environment variable, if it's not set to this one, okay, code blocks MinGW under bin, as you can see we have this GCC, G++, all the GDB, everything is here under MinGW bin. So you have to have this directory in your path variable to be able to run these GCC, G++. So minus version, do we have the version, or just minus v? Yeah, so it's, yeah, actually it's showing where it's executing. So program files, code blocks, MinGW. So I have the GCC correctly pointing to the places that we have installed. Now what I'm going to do is, let's compile it with this minus GCC minus G minus. So by the way, let me change the font of this so to a larger font so that you can see better. Alright, so this is my command prompt. So the file that I have here is the test.c. I'm going to produce a test.exe executable, test.c. Now, in order to link those, so when you do it like this, it's not the, you need to give the library file names here, -l, then they should be given in a certain order. Let me try to. So when you do it, actually, you get lots of errors at the link time, not at the compile time. So all these errors we get here, undefined reference to glfw set window. So during compile time, there was no problem actually. So these are, as you can see, the errors we get here is in our temporary object file, which was compiled, but during linking, these functions that our our code refers to, there is no compiled versions of these functions. So we need to link them. I think it was like -l OpenGL 32 -l GLU 32 or glue. Let me just try to find in my email. MinGW compile compile -l OpenGL 32. I should have it in my emails. Compilation problems, maybe. Let me try to find it. I should have. Yeah, glue 32. It should be glue 32. Not this one. Let me try. Probably minus glue 32 and GLFW. GLFW. I should have the GLFW3. So yeah, the errors have changed to something else, so I need to, probably it's the, do I need glue 32? I should read the manual directly, but yeah, I'm trying to find a shortcut here. OpenGW compile. All right, so I should have it here. No, not this one. Yeah, like this. First, OpenGL 32. Oh, there. Okay, minus. This is for glut GLU 32. OpenGL 32, GLU 32. Maybe GLFW3 should come first. GLFW3. Or just GLFW. No, it should be 3. So it gets the files correctly. WGL glue 32. Or is it when? It should be. I should be able to find those. No, that's not OpenGL 32 when it's like this. No. Let me quickly try to find it. GLFW. I should. No, it's the same thing. Okay, I did it in OSX previously. Let me find that, and I'm going to put it maybe as a separate video later. But I mean, or just let me just take a look at GLFW website. Yeah, how to. There should be documentation here. So here's a simple code, or just GLFW NGV compile. So I should have it here. How I link it? Yeah, it's here. So GLFW should come first, and OpenGL 32. GLFW 3. need OpenGL glue. Okay. Glue 32. I couldn't solve this problem. I will solve it, and I will just write how I compiled it. I will write the compile command on the announcement, so I will be able to do that. So it's also using, there are different, these GDI 32, kernel 32, which I don't think I have ever used before. I don't think I need them. GLF, maybe I should just also GLFW3 glue 3. Yeah, glue. So this is the last time I will try. So maybe here. No, this is just a general answer. So I will find this. I will find a solution to this. I should probably have a makefile in my maybe or readme here that I wrote to myself. But I will find it and I will solve this problem. Okay, we will. But if you take a look at the code and what it does, okay, is in this main function we have this window which is going to be our OpenGL context, and we have a vertex buffer which we are going to send our vertex data to the GPU. If you're going to write some program on the GPU, these are our shaders. When we compile these shaders and link them, it becomes our user-defined program that runs on the GPU. So if you look at these things, these variables, they are nothing but integers, okay? All these variables that refer to certain objects. If we have objects on the GPU, we cannot have a direct pointer to them. We cannot access the memory on or any object that lives on the GPU is not possible to access them from the CPU directly. So in OpenGL, what we use is, we use unsigned integer IDs to refer to them in our program. So these, as you can see, they're all integers. This says it's a vertex buffer, but it's just an integer ID. So the way we do that in OpenGL is we just call the OpenGL function that tells us, give me a vertex buffer object on the GPU. So it actually allocates a vertex buffer with certain size. So it allocates an array on the GPU with certain size. But we don't have a pointer to that array on the GPU because, as I said, as the program that is running on the CPU, we don't have access to direct GPU objects. But this function that I ask to get me a vertex buffer gives me a handle to that vertex buffer as an unsigned integer, which I can use in other OpenGL functions to set that buffer. By using that buffer ID, we can send write data to that location on the GPU. Okay, so all these things, all the objects that reside on the GPU, they are accessed by unsigned integer IDs, and these IDs we don't give them ourselves. For example, if you take a look at this vertex buffer object, how it's referred to, here, as you can see, we use this function. It's GL generate buffers. So this GL generate buffers is like generates a buffer and it's the ID. It just gives us an integer ID at this point. It just declares a buffer object on the GPU, and this one is just, I want one buffer object. It generates this on the GPU and gives us an integer ID at the end for us to refer to. Now, these functions, when I say GL bind buffer, GL array buffer, and give this integer ID that is given to me, at that point, this vertex buffer its type is set to be an array buffer. And when I say bind buffer, whatever OpenGL functions I'm going to call subsequently, they're going to be referring to that object on the GPU. And here, this function is the function that sends that data, copies them uh, to the place where allocated on the GPU. So this buffer data function says that I have, so if you look at this vertices is just an array that I have on the CPU. Okay, so if you look at vertices, it's nothing but, so this is vertices. I have 1, 2, 3, 4, or these 3 by 3. Actually, these are the first 2 are XY coordinates. The last 3 are RGB colors. So a vertex data is nothing but 5 floating numbers, and I have 3 of them. So this data, these floating point numbers here, are actually sent and copied to an array buffer on the GPU with this single function call. So where were we? Here, vertex buffer. Yeah, let me call. And this is done once, vertex buffer. We don't do that at every frame. If you look at this vertex buffer object, so this part is done outside the loop. So the code that you see here is run at the initial stages of our, I mean, as a once only at the initialization of our program. After our program starts running, it goes into this infinite rendering loop in which we are going to either, I think what we are doing is rotating. We are rotating a triangle, if I'm not mistaken. So this test program, what it does is it draws a triangle and it rotates it around either origin, or we can try to rotate it, for example, around one of its vertices. And all these matrices you can see here is doing these things. Okay, this rotate function gets the current time and rotates, multiplies the current model view matrix with this rotation function that it generates. Okay, we are using this rotate function from that linmath library that I had in the same directory. I'm going to share all these GLFW examples with you. Hopefully you'll be able to compile and run them with no problem on your own machine. I'm going to write that compile command to compile them correctly on a Windows machine using MinGW 64 bits. Okay, I'm going to find that after the class today, and I'm going to share with you on the class. So, as I said, what this single function sends the entire contents of this vertices. As you can see, it gets a pointer to some memory location on the GPU, and it gets the how many bytes we are going to be sending to the GPU. It's also given as parameter. This static draw function is going to say that it's going to be used, that array, the data in that array is going to remain static. Those are our main vertex data objects. We may translate them, we may move them, but the original vertex data is going to remain static. I think that's what this, there may be different types of arrays that you can allocate on the GPU, and this GL static draw is one of them. This is what we usually, I haven't used any other parameter other than this. Now, so this part, we sent our data to the GPU in one shot. And after that, we create, at this point, we have our vertex shader. This vertex shader text was nothing but this, okay? It's some code in GLSL. It's saying there's a uniform matrix called model view projection matrix. There's an attribute for our vectors, which is the color. And there's another attribute for our vertices, which is the position, which is a two-dimensional vector. So colors are three-dimensional, positions are two-dimensional, so it's a 2D graphics example we have here. And here we define a varying attribute, varying variable, color, which is going to be interpolated. If you, for example, give different colors to the vertices of the triangle, in which I believe that's the case here, one vertex is red, 1, 0, 0, the other vertex is green, and the third vertex is blue. Okay, so I have our red, green, blue vertices assigned to my triangle vertices, and these are the positions, 2D positions of my vertices that are in a viewport with coordinates between -1 and 1. So here the vertex shader, the only thing vertex shader does is whatever the model view projection matrix is, it multiplies it with my vertex position, which was a 2D vector, by the way. It converts it to a 4-dimensional vector, because in OpenGL in 3D graphics, all our model view projection matrices, they were 4x4, so it's in a 3-dimensional environment. So basically we set the third dimensions of these vertices to 0, their z coordinates become 0, and this is their this is their h value, the homogeneous coordinates, they are set to 1. So that's the only thing the vertex shader, vertex processor does. And another thing is it sets color. This color attribute here is set to the vertex color. Whatever the attribute of the vertex is set to this color for this vertex. But it's going to be automatically, since it's defined as a varying variable, it's going to be automatically rasterized by the GPU, and therefore the variable we have here as color for a fragment will be the interpolated color we have. And the only thing that fragment shader does is set the default output variable. By the way, these GL position and GL frag color, these are the default variables that you have to set in a vertex shader, in a fragment shader, but these are in early versions. In the newer versions of these programmable shaders, even this part, there are no built-in variables anymore. Everything is user-defined. You just define input and output variables for each shader. Here goes. I'm going to show you some examples, but you can use in your assignment, for example, you can use these early versions in which there are these built-in variables. It's just setting the color of the fragment to whatever color that is interpolated. It sets the color to that. So in the color, the fourth dimension in the color is the alpha RGB A value. But let's go back to here, what we do. So the vertex data is sent to the GPU. We call a GL create shader function, saying that this is going to be a vertex shader, and we this vertex shader, it becomes nothing but another unsigned integer ID. So what was this vertex shader? It's nothing but an integer, unsigned integer ID. So when you call this create shader function, it creates some object, on the GPU, but your handle on this object is nothing but an unsigned integer again. So you use this unsigned integer when you are for example, calling other OpenGL functions, saying that GL shader source, the source code for this vertex shader is this vertex shader text. And you call this function compile shader, you compile it. Similarly, you compile your fragment shader. Then you create a program that is going to use both of these. This program is nothing but a specific forward rendering pipeline, a user-defined forward rendering pipeline. So this is what a program is called in the context of OpenGL program. When you say GL create program, it does nothing but saying, again, creates an empty object on the GPU part, which is going to be hold these links to those program parts, different vertex fragment shaders. But on the CPU side, this program again is nothing but an unsigned integer. When we say GL attach shader, as you can see, we just give two integers. Attach this vertex shader, which is an unsigned integer ID, to this program that I created. Attach this fragment shader to this program that I created, and link the program. And after you have the link program, whenever you say GL use program, I should have a call that says GL use program. GL use program. Yeah, when you say GL use program, you tell the GPU to use your specific vertex and the vertex and fragment shaders that you have compiled and installed on the GPU at that point. So from frame to frame, or within even a single frame, you can switch between different programs. For example, you can render one object in grayscale, while you can use another program which computes color for different objects. So in the same rendering loop, you can use multiple programs for drawing different things on different parts of the screen. For example, I mean, even on top of each other, you can say draw this object completely in grayscale, like in black and white, but these other objects, let's make them color. Okay, so you can have a vertex shade fragment shader in which the color is computed in grayscale, and another vertex fragment shader in which the color is computed by using real colors, and you can use that. You can switch between them by using this GLU's program even within a single frame. So, and we also have this at the initialization. These are our handles to variables that are within our vertex shader. Look at these. From this program, from this vertex shader program, get the location of a variable named MVP. So we had variables. As you can see, we have variables that are defined here. MVP, vertex color, vertex position, which are these attributes. And since these are variables defined again on the GPU, these are going to code that are going to be on the GPU. How to send data, for example? How do we send this matrix information that we compute on the CPU at every frame to the GPU and assign it to this? Copy this into this variable named MVP in our machine. So the way to do that again is to get handle a pointer to those, and which are nothing but this MVP location, vPost location, vCall location. What are these variables? Let's take a look at one of them, MVP location. It's nothing but an unsigned integer. This case is an integer, not unsigned integer. But these handles to these variables, they're also just integer handles. You get that location from your code, and at the end, and let me skip those parts, but what it basically does is it says that this location that you get here, the vertices, the vertex attribute pointer, the first two values in your vertices array was actually referring to this vPost variable, vertex position in your header, and the last three attributes, which were those RGB colors, they are your they refer to this variable. They are going to be automatically copied per vertex at every which is going to use those vertex buffer objects actually. And within your animation loop, you can change the viewport if it's resize, for example. If you resize your window, you can get window width and height at every frame and change your viewport so that the entire image is resized within your viewport. This function call clears the entire screen to background color. So every frame, we're redrawing the triangle from scratch. These are your model view projection matrix finding. You say use my program, send my MVP to the GPU, and this single function call draw arrays triangles draws your triangle in one shot. Since we use double buffering, we call this swap buffer function. And this poll events is a function to call for keyboard mouse events. So at the end of every frame, so this while loop is run 60 times per second, and every frame we are asking whether did the user press certain keys. Has the user pressed certain keys, or has the user done some mouse action? So this is that poll events function. And after, for example, this one is just saying GLF window should close. It's asking all the time whether is there an event that should close this window. And this can happen, for example, we have a keyboard callback. As you can see, this is my keyboard callback that I had written. If the user hits the escape key, so if we press the escape key, what we do is set window should close to true. So this one just signals that window now should close, and it calls this to this GLFV system. And if this signal is set, okay, window should close, at the next loop this will be true. It should close, and not will be false. Therefore, that's the place where we exit this while loop. by the press of the escape key. The window is destroyed by GLFW, by probably some housekeeping is done, freeing some variables at that point. We terminate our GLFW program and exit our program. So this part is while we're exiting our application. So if you're able to run this code, as I said, I'm going to compile and run it on my machine, and I'm going to show you how it's done on AutoClass. You should try it at home, and you should see a triangle which is rotating around origin. It should be a colorful triangle where different color, the red, green, and blue colors are interpolated along the surface of the triangle. And you can try with different things. For example, what happens if you change this code? For example, instead of having color here, what if I call 1.0, 0.0, 0.0 here? So you can try different things, which will make, for example, if I do this, the entire triangle will just be red. Nothing else. It's there. I will not see any interpolated colors. I will just see a red triangle if I do that. Okay, so that's it from me for today. We are going to continue with the slides, but I went over many of these functions here that are already on the slides. I'm going to go over more examples. This time, hopefully I will be able to compile and run these different examples, and I'm going to show them to you on Thursday. Okay, I will show you a more complicated example. I have a nice spotlight example with a desktop lamp. I'm going to show you that. There is this Marty and the Rocks example that I want to show you. I'm going to also put them on AutoClass as well. All right, so do you have any questions? It may be too much at this moment to just all these functions, learning all these things. You don't need to memorize any of these functions. You will probably just start on these templates and modify them when you're coding these OpenGL. But I will also upload a text file to how to set up OpenGL and GLFW on Ubuntu. I will also share that with you, all the links, and I'll also share with you the programs. I will upload them on AutoClass under week 11. All right. All right. I will stop recording now. Okay, hello again everyone. Let me put this at the end of the video. So just after the class ended, I was able to find the solution to that compilation problem in a minute. So it turns out that our order of glue32 GLFW was correct, and we have to include OpenGL and glue32 like this. It turns out that we really need this GDI32. So if you compile it with these parameters, it compiles with no problem. So I didn't do anything to our GLFW glue installation. So our installation, copying them into include lib directories, everything was correct. So here's how you should compile it. I'm going to post this on AutoClass, and when you run your program, as I said, it just gives you a rotating triangle with one vertex green, the other blue and red, and the colors are interpolated nicely along this, and you have, in this simple example, nice smooth animation of a rotating triangle. Okay, so I'll put this at the end of the video, and hopefully you will be able to, when you watch this video at home, you will be able to compile and test it correctly on your own. Okay, bye-bye.